Hello everyone, we're team number 30 and today we're presenting the semantic segmentation for urban scene images. Semantic segmentation is a task of labeling each pixel of an image with a corresponding class of what is being represented. Our problem of interest lies in the specific task of segmenting urban scene images, which serves as the base for automating driving algorithms. Indeed, urban scene images has intrinsic positional patterns. For the images captured by car cameras, roads and cars are usually centered, with people walking at left and right-hand sides in the image. In 2015, Long proposed a CNN-based architecture called FCN that allows input image to be arbitrary size. FCN further motivated researchers like Chen to develop DeepLab to mitigate resolution reduction during pooling, multi-scale object problem, and produce better object boundaries. On the other hand, researchers use positional patterns of urban scene to normalize object scale. However, there has not been a thorough and optimal solution that aggregates the results in both sides. In this project, we would like to develop an integrated model based on the most novel discoveries in the field. We would incorporate structured information for urban scenes. Meanwhile, we try to maintain the computational efficiency by advancing the model design. We use a large-scale urban scene image dataset called Cityscapes. The total dataset captures city streets and is split into a training set with around 3,000 images and a test set with 500 images. The dataset is finely annotated with 19 pixel-level classes. Our task is to perform a pixel-level semantic segmentation using the original images as input. We perform data augmentations like random horizontally flipping, random scaling, Gaussian blur, and color jittering to increase the diversity of data and avoid overfitting. Our approach towards solving the problem could be divided into 3 steps. The first step is to utilize DeepLab version 3 Plus as our strong baseline model. DeepLab version 3 Plus helps obtain a sharper object boundary with an encoder-decoder system. The encoder module reduces the feature maps and captures higher semantic information, and the decoder module gradually recovers the spatial information. Our second step is to capture characteristics in urban scene. The figure shows that the class distribution has a significant dependency on the vertical position, which reveals the possibility of improving the model based upon that. The HANet captures such spatial information and is a flexible add-on module, so we implemented it between layers. Our third step is to use WASP for the pooling layer. For standard DeepLab version 3 Plus, ASPP layer is used to maintain larger field of view and resolution during pooling. However, it suffers from large computation time and storage. Replacing it with an advanced version WASP helps resolve the problem, and this forms our final model architecture. For evaluation metrics, we use IOU score to measure the overlapping between pixel-level prediction and ground truth. Our key finding is that our 2 modifications both outperform baseline in the mean IOU. HANet demonstrates the ability to capture spatial information with increase in wall, fence, and bus per class IOU score. However, there is still room for improvements for classes like light. Also, with less parameter in WASP, the average minute per epoch reduced from 4.5 to 4, without harming mean IOU score. In the model prediction, adding HANet reduces the noise, as shown in the right corner, according to the height-driven information. Also, data augmentations helps identify objects under dark lightness, just as you can see in the left corner here. In conclusion, vertical precision-based HANet is effective to boost model performance. However, it has difficulty in identifying taller objects across different sections. And WASP generates similarly better results, but require less memory and time. With that, we end our presentation. Thank you so much for your time.